GAN is concerned, D acts like a simple binary classifier. It looks at the data from G, which is outputted by G, and also the real data, which is obtained from our original data set. These are the two main inputs into the discriminator, and then it tries to mathematically determine which is real and which is fake. So it's basically a binary classification task between two classes, real and fake. So its goal is to maximize its ability to correctly label the data as real or generated. So, in mathematical terms, D is trying to maximize the probability of correctly identifying real and fake data. Now, the interesting part is how G and D learn together. So, they are in a continuous loop, as we'll also see in the training loop later in the Jupyter notebook. So, G creates data, D evaluates the creation of G and sort of gives its feedback, and G adjusts its creations based on this feedback to create more realistic data. So it's like a teacher student relationship where the teacher is guiding the student, teacher is D and student is G, towards creating more realistic and convincing work. So over time, G gets so good that D can barely tell the difference between what is real data and what is fake data. So this process, although I describe it in sort of a simplified way, it involves many complex algorithms and neural networks, as we'll see later. And the end result of all this is that GANs can create highly realistic data, which are useful in various applications from art generations to simulations and so on. So GANs currently, this is the explanation of how GANs work, put into three simple lines. So generator generating, discriminator evaluating, and there's a continuous feedback loop. So GANs have a wide array of applications. They are used for creating realistic images, text, data, video, and even audio. So they are innovating in the realms of art, design, and entertainment. And they are also creating revolutions in the fields of healthcare and scientific research, which shows their versatility. And one such example we'll be seeing in the coding part today. Also, we'll see a small demo about conditional GANs. So, conditional GANs are a specialized variant of GANs which generate data based on specific conditions or categories, more like class labels, making them ideal for targeted data generation tasks. For example, if there's a certain kind of lung disease whose chest x ray image I wish to produce, then I can train a conditional GAN on a certain labeled data set with labeled images of lung diseases. And the model can then produce a new image depending on what kind of disease simulation I want. So, this ability to control outputs can open up a lot of new possibilities for having desired data. Now, there are several other different kinds of GANs as well, and each have unique characteristics. Like deep convolutional GANs, which are DC GANs, one example of which we are going to see later today. They specialize in image creation. Style GANs, they excel in high quality image creation, and cycle GANs are used for image to image translation tasks. So, in the TensorFlow documentation, there are some code notebooks about creating dream images and translating the styles of one existing image to another. So each type has their own applications and advantages, and some interesting applications which I've come across is transferring one artist's style from his painting to another painting. So these can be used in many other productive tasks as well. Now, the applications of GANs in art and design. In art and design, GANs are revolutionizing the industry and they're assisting in creating new artistic styles, digital artworks, and even concept generation. And they are mainly useful in the fashion and interior design industries where they assist in creativity basically. And they're also important in the entertainment sector where they are used for making realistic game environments, movie effects, and VR experiences, and even new music and audio experiences, like translating or transferring one artist's work to another artist's work, and even creating audio clips of people who are no more with us. So these are quite revolutionary applications of GANs. In healthcare, especially, GANs are proving to be very invaluable. They are helping to create synthetic medical images for training, which is a big step towards data privacy. And they also help in drug discovery and improving diagnostic tools and patient care. So, their potential in personalized medicine is also quite huge. But there are ethical considerations to the usage of GANs as well as with other AI tools. So, the main consideration is creation of deep fakes and misinformation, because GANs can literally be trained to create anything if we have enough computational resources. There can be fake videos circulating for triggering political conflicts. So it's important to develop ethical guidelines for the usage of GANs. And as far as training GANs is concerned, there are certain challenges which GANs face, the main two being substantial training data requirement and high computational resources. And there's also a risk of biases being flown down into the generated data, and it's difficult to control and understand the outputs because AI is often regarded as a black box, and it's important to understand the outputs and the internal workings if we wish to remove the biases. So, addressing these challenges is key to maximizing the benefits of GANs. The future trends in GANs, they look quite promising. We expect to see continuous improvement in data quality and diversity, and there's likely to be an expansion in personalization and user experience, and also integrating it with other AI technologies for more innovative solutions. Also, efforts are being made to reduce the computational power which is required for training GANs. So, in conclusion, GANs are a very transformative force in AI and technology, and there's diverse applications across industries spell out their importance. But there are many ongoing developments as well as ethical considerations which remain crucial for their responsible use. So, now that we have seen what GANs as a whole are, we can move on to the notebook for seeing an example of an application of GAN and how we can train our own model. I just change my screen. So I've mainly borrowed the code from TensorFlow's documentation. They have pretty good documentation for different kinds of GANs. So first I'll be uploading certain image data which I have um, taken from the NIH chest X-rays data set. For demonstration purposes, I'll not be uploading too many images, and so the outputs won't be at par with really high levels. So to give a high level overview of the code, there are some imports which have been done initially for data pre-processing. This cell is mainly for data pre-processing. So OS is mainly for dealing with file paths in Python, OS module. So this is the root directory which contains all these images. And this is one function for pre-processing the images. The main steps which have been taken here are: this for loop is finding all the images with a PNG or a JPEG uh, extension, and this this line is basically for joining the path of the file, for creating the path of the file by joining the directory name to the file name which has been extracted from here. And this line is for resizing the images to 52 cross 52. Now, why this number? This number is useful for the model which comes later on in the code. And resizing every image to a common shape is useful for maintaining uniformity. And this creates um, an array of all the images represented as a matrix of the pixel values which they are composed of. So this image dot open basically loads the image as a matrix of, as a 2 by 2 matrix of pixel values into this img variable. And this basically adds this img, converts this into a numpy array, np is numpy, and it is appended to this images list. So now the images are loaded into the train images variable. Now I'll reshape all of them for checking whether all of them are of the same shape. I'll still run this reshape command, and I'll convert the pixel values into a float 32 data type so that it becomes easier for Python to deal with the numbers later. Now we can see that the shape of the first image in the train images variable is 52 by 52 by 1. 52 is height, width, and 1 is the number of color channels, which is 3 if it was a colored image, which is RGB, and if it's a grayscale image, it's going to be 1. And this just shows that we have 66 images, the size of the thing, and 52 by 52 by 1. Now, this line is important. It's called the process of normalization. And this one is basically converting the pixel values, which originally range from 0 to 255, to a range of -1 to 1 by doing this mathematical operation here. So normalization can be basically of two types. One can convert it into a range of 0 to 1, and another can take it from -1 to 1. We are using -1 to 1 here because the model which will be training below uses a tanh activation function in its final most layer. And tanh activation function outputs values in the range of -1 to 1. So it becomes easier for the model to deal with this image because of that. So normalization also helps to standardize things across and remove biases. So this is an important pre-processing step. Now buffer size and batch size are two constants which are important for model training loop below. And these are a few more imports for training the model as well as later plotting the results that we'll get from the model. Image.io and Globe are both for dealing with pictures, and this is for visualization, and these two are for models. Now, this line is also important from the model training point of view because there are two main objectives of this line. Three main actually. First one is to convert this training images array which we had created above, which contains all the images, into a tensor, because TensorFlow models, as can be interpreted from the name, they deal with tensors better. Tensors are a data type which are similar to arrays, but they have certain properties which make it easier for models to process them, for models created by TensorFlow and Keras API to process them. Second objective it achieves is shuffling. Shuffling is to prevent the model from inadvertently learning sequences from the order in which we are uploading images into it, because the sequence here does not hold any inherent meaning, so it's not useful to make the model learn that. And the third objective is batching. So while we have uploaded only 66 images, batching won't at all be useful here. But in reality, there are like thousands of images uploaded. So batching helps to streamline the training process later. It's like divide the batch size we had above was 256. So it's like dividing our entire training data set into subsets of 256 size each and passing them into the training loop. So this is a very important line for the model below. Now, finally, we come to defining the model architecture. So I'll go through one line, line by line, to explain how the model architecture is composed. So this cell defines the generator model. As we had seen before, a GAN has two components, generator and discriminator. So this is the first component. This first line, tf.keras.sequential. Sequential is basically a function which returns the model object into this model variable. It's a function for creating models in Keras API, using Keras API. And it's initially, when we just have this line, it returns an empty model with no layers and no input output anything into the model variable. Dot add function is the function used for adding subsequent layers to this sequential model. So the first layer that we add is a dense layer. So dense layer is basically a fully connected layer. A layer means something which is composed of neurons or computational units, anything which is composed of those things. And the parameters are basically used to configure what kind of a configuration of neuron we are uploading into a model, and various other parameters like what input shape can it expect and what size of the data can it expect, and so on. So dense layer is one such kind of layer called a fully connected layer. And 13 cross 13 cross 256, this is the number of neurons that it needs to be composed of. Now that this 13 has a certain relation with the 52 cross 52 image size that we had reshaped our training images into earlier, as we'll see later down in the math of this model. Now, use bias false is another parameter, and input shape equal to 100 is basically the size of the noise input vector that this model can expect above later when we are training the model in the training loop. This input shape parameter is present only in the first layer of a model, and the other layers, they don't expect the input shape because they can know from the previous layer of the model itself what kind of input will be passed down to them. The next two layers are kind of pre-processing, not pre-processing but processing the output of each layer, so that the next layer can make proper advantage of the output it's getting from the layer previous to it. So these two are batch normalization and leaky ReLU. Normalization, as we discussed above, the objective is quite similar, and leaky ReLU is called an activation function. So activation functions are, simply put, nonlinear equations which are introduced to remove linearity and bias from the model outputs. So leaky ReLU is one such kind of nonlinear function, f of x, where x is basically the output which comes down from the dense and batch normalization layers. There are two kinds, ReLU and leaky ReLU. Leaky ReLU is used here. Now, instead of going deep into the maths, the main reason for using leaky ReLU and not ReLU here is so that the neurons don't die. Neurons dying means them not giving any non-zero outputs at all. So what happens in ReLU is, often when the input to it is negative, the output from ReLU layer is zero, which is known as a neuron turning off or dying. Leaky ReLU prevents that by outputting a constant instead of zero directly. So that helps to keep the gradient flow alive in this generator model, which is quite important for a generator. The next layer is reshape layer. So it's basically the output from a dense layer is a 1D vector having these many values, and we want to reshape that into a 3D matrix with 13 cross 13 cross 256 as its architecture. And this assert statement is basically a kind of checking statement to see if the if condition which has been stated right after assert is satisfied or not. The next layer is the convolutional 2D transpose layer. For those who are familiar with CNN, conv 2D is a very common layer, but this one is the exact opposite of what a conv 2D layer does. So, simply put, the conv 2D layer's objective is to do downsampling, which is to reduce the size of the image by a certain factor as the image array goes down the model. But the conv 2D transpose, its objective is to upsample the image, which is to increase the size of the image by a certain factor as it goes through the model. So this is quite intuitive because in this model we are originally beginning with a noise vector which literally means nothing, which is simply 100, the size that we took above 100, a 100 element 1D array, and we need to gradually define the various details of the image that we wish to create and fine tune it, and also expand the spatial dimensions of the image, which can only be done if that original vector's dimensions are increased by upsampling it. So that's why this name transpose, which means opposite. So conf 2D transpose is a very important layer for that. Now 128 is again the number of neurons which are present in this layer. 5 cross 5 is known as the kernel size or the filter size. So simply put, a kernel or a filter is a matrix which travels over the image is also a matrix because we had reshaped it into this size before. So this kernel basically travels over the matrix, spans the entire matrix depending upon the stride, and gets new values depending on certain multiplications and additions, and fills them out into an output matrix. So strides 1 comma 1 is how many steps the kernel or filter will be taking to span the image. If it was 2 comma 2, then the filter will just skip one step and go from 1 to 3 to 5 and so on. But if it's 1 comma 1, if it simply goes from 1 to 2 to 3 and so on. So if the stride is 1, the output is going to be the same size as the input image. If the stride was 2, then if it was a conv 2D instead of a conv 2D transpose, the size would have halved. So this is the basic intuition behind strides. Padding being same is another hyperparameter, which basically means that when this filter, its center is on a corner or an edge pixel in the image, it cannot be spanning. Some part of the filter will basically be outside of the image, but padding being same means that the model compensates for that by padding the original image with some zeros, so that the output image's size is same as the input image's size in case the stride is also 1. Use bias being false is also another hyperparameter. So now, because the stride here was 1, and as I explained the other hyperparameters, the output shape is going to be the same, but the number of input channels is always the same as the number of neurons. So that changed from 256 to 128. Again, these two are processing layers that we have after almost every neuron filled layer. Now, coming to the next one, we reduce the number of neurons, 64, and so the output now also has 64 channels. Now, the difference between this one and the next layer is stride being 2. So, stride being 2 is basically going to double the size of the image. Double the size of the image, which was inputted from the previous layer to it. The size which was inputted was 13 by 13. So as we can see in the assert statement here, it has become 26 by 26. And now coming to the final layer, which is identical to this, except that it has just one neuron, which because we are expecting just one channel, one grayscale image. And even the stride here is 2, which means that it has now increased to 52 by 52 by 1, which is same as the original image size to which we had reshaped our training data to. Now the difference in the output layer and the other layers is we have an additional activation inbuilt into the hyperparameters here, which is this tan h activation as I had described before. It's mainly for outputting the same values as the normalization values that we had pre-processed the image into before. So this function is basically returning the model to us. Now we'll run this function and get the model into this generator variable. And just for demonstration purposes, we'll just pass in a random this line is creating a random noise vector of size 100 elements, and we'll just generate an image using this random noise vector. Now one hyperparameter to set here is training equal to false, so that the model doesn't end up learning from this noise vector because it's literally nothing. And we can create it as true as well if we want it to be in its learning mode, but here we want it to be in its inferential mode. And this line is basically for showing the image generated. So as we can see here, it's nothing can be interpreted from this image because a simple noise was passed into the model, and the model has not been trained yet on any kind of input data. So this is what is expected from it. Now, coming to the discriminator model, for those who have done classification tasks before, discriminator is nothing new, but it's just a binary classification model classifying an image into 0 or 1, 0 being fake and 1 being real. So, this is again the sequential API that we are using for creating the model. The next one being conf 2D here, not 2D transpose, because here the input is going to be an image and we need to downsample it into a probability basically of it belonging to one class or another. So we need the conf 2D here and 64 neurons, again 5 cross 5 kernel size, which is a very standard kernel size. And again, we have defined the input shape to 52 by 52 by 1 because we are going to pass the images generated by the generator into this model. Now, this is the same leaky ReLU function, and this one is new over here, which is the dropout layer. Now, the main objective of dropout layer, put simply, is to simply turn off neurons at random inside the model. Now, why is this required? There's a term called overfitting, which is when the model becomes overconfident of its abilities. It, instead of learning the patterns, it simply memorizes the data which we are feeding it with. So it cannot generalize well to new test data, which is not useful for us. So at random turning off neurons can help in reducing overfitting by preventing overgeneralization while training. So turning off neurons makes sure that nearby neurons do not learn the same thing. So this number point 0.3 is, it means that 30% of neurons at each training cycle they'll be randomly turned off. So we do this after every conf 2D layer, and this 2 comma 2 is basically halving the size of the image after every conf 2D layer. And this final one is dot flatten because a dense layer or a fully connected layer basically expects a flat 1D vector like the noise that we had passed in the previous model. So dot flatten is turning the 3D image array into a 1D array, collapsing it. And dot dense with a 1 in it, 1 means it expects a single output. A single output means just a single probability value. And this function is returning the discriminator model. Now we can test out the decision that the discriminator gives on the generated image. Generated image is this one, the random image. And this will again be a very random value, which is this over here, because obviously the discriminator hasn't been trained yet. Now, coming to defining the loss functions and the optimizers. So, binary cross entropy is a very commonly used uh, loss functions for any kind of classification task, binary classification task. Now, going into the mathematics is not important, but what exactly is a loss function? It's kind of a reward system for the model to know whether it's doing a good job or not. So the models, any kind of model's main objective is to reduce the cost or loss function after every training and update its weights and parameters accordingly so that it goes into that direction of convergence. Convergence meaning reducing the loss of the model, loss that the model entails after every prediction. So this is one such kind of loss, and this parameter from logits equal to true means it takes the raw values before the activation variation. The activation function is applied on it. So this parameter is mainly passed in for optimization purposes. So we'll be defining the discriminator loss and a generator loss. So these two are different entities because the objectives of generator and discriminator are two separate things. The generator has to generate an image and get more proper at doing it, and a discriminator has to label an image as real or fake. So since the objectives are different, we need to define the loss and reward system for them differently as well. So for the discriminator loss, there's going to be a real output and a fake output. So real output is going to come from this training data images that we have here, and fake output is going to come from the generator. So these are the two input parameters. Now, real loss cross entropy is basically, if we try to understand it simply, it's like a subtraction, a modified subtraction with with some functions applied to each value. But yeah, it's like finding the difference between what we want and what we have. So this parameter here, tf dot ones like real output, is creating a 3D array full of ones but having the same shape as the real output. So we are basically taking the difference between the real output and this fully filled with ones array, because if a image is real, then the discriminator is supposed to predict it as class 1, which is real. And we want to see how good it is at doing that by finding the difference. The lesser this value of real loss, the lesser the difference, the better our discriminator model is. Similarly, for fake loss, a model has to label a fake image, a generated image, as 0. So we want to compare how close a fake output is to um, a matrix full of zeros. So zeros like is basically creating this matrix with the same shape as this fake output. And to correct myself, real output and fake output are not the raw images, but the probability verdicts on these images given by the actual discriminator model. So these inherit the shapes of the images, but yeah, they are the probability verdicts. So the total loss for the discriminator model is simply going to be the summation of these two losses, because we want to reduce both. We want the model to become better at predicting which one is real and which one is fake. So this is what the discriminator loss is. Now coming to the generator loss is simply how good the generator is at fooling the discriminator. So it's like it needs to output an image which is originally fake, but it's very much like a real image. So the discriminator should be fooled into classifying it as a real image itself. So here, instead of comparing fake output to a zero filled array like fake output, we'll be comparing fake output to a one filled array like fake output, so that this is what it's supposed to fool the discriminator into believing, that a fake output is to be classified as one or real. So this is the intuition behind generator loss. And coming to the optimizers are simply for helping in the learning process of the model, and Adam is the optimizer we'll be using here. tf.keras offers a lot of optimizers which we can check out in the documentations. I've tried out like 9 varieties, and Adam is a pretty good variant. And 1e minus 4 is a pretty standard learning rate for Adam. And if you have too high a learning rate, then the model doesn't converge and it overshoots. and there are any results that come not applicable. So 1e minus 4 is a good choice. This cell is simply for recording all the checkpoints so that somehow if we lose the model training midway, then we can simply recover that from the checkpoints and we don't need to start from scratch. Now, to define some more constants, epochs being 50 basically means the number of times the model is going to see the entire training data set as a whole, not the batches themselves, but the entire training data set. And noise dimension being 100 is basically the random input vector size that we had decided we'll pass in earlier. And number of examples to generate is simply a certain number of padding that we'll append to it later. And we are seeding this normal value for reproducibility, so if we run it twice or thrice, it's easier to visualize since it will yield the same random value. So now coming to the actual training loop, we had just defined the models before, we have not trained them yet. So we have the models, but they need to be fit to our training data for them to yield images as we expect. Now this is simply an annotation to show that this is a function to be compiled. So this is a train step where we are creating the noise vector first, and tf dot gradient tape is a very standard way of defining training custom training loops in TensorFlow. So first we'll be generating images from the generator, and training mode here is true because we want to learn it from the data we are going to pass into it. Now the real output is going to come from the images that we have here, and the discriminator produces a verdict on them. Fake output will be done on the generated images. We compute the generator loss and the discriminator loss. We compute the gradients of each. Gradients meaning in which direction should the model now change its parameters for nearing convergence. So this is basically a function which is provided by gradient tape for optimally calculating gradients without too much of wastage of computational power. So internally it keeps saving gradients, keeps saving the function of gradients, and it doesn't have to recompute. And we apply the optimizer and the gradients together and zip it together for optimizing the training variables and making it converge slowly. And this is another part of the training loop where the epochs come in, the actual data is passed into the model. So for each epoch, which is what this for loop does, we are recording the time. So for each batch in the data set, we are going to run this train step function on it, and we'll keep displaying the images. It will be sort of a GIF like thing, and we'll keep saving checkpoints as well for so that we don't have to we can easily restore in case we lose the training progress. And yeah, these are mainly images, I mean code for recording, and this is the main training step, the training loop. And this is simply a helper function for generating and saving images, again for keeping a record. Now one key thing here is when we are saving the images, we are doing the normalization step in reverse so that we get the pixels back to their standard range of 0 to 255, and reasonable images are created. And also the training is set to false here because it's inference mode. Whenever we are making predictions on the test input, we are always going to do that in an inferential mode because we don't need to learn it from the test input. So this is the training loop. Because I'm using a T4 GPU here provided by Google Colab, so I believe it will be kind of optimized. Now, I don't expect the results to be very good because I've only trained it on 66 images for because of constraints. But the images that were there just before this, they were something I had run on around 2,000 images. This may even be very close to the random one that we had created much before, but yeah, this is sort of how the concept works. Now, as I had said before, the images are not at all that great because it's just 66 images. But if we run it for more epochs and we have like thousands of training images, they would be much like the lung images that we had before. Yeah, I have them. I still have them from my previous training loop, and they are because the resolution is less here, so they are a little smudged. But yeah, they are quite close to the images we have originally. And these two code cells are simply for restoring the checkpoints and displaying the images. Yeah. So now that we are done with DC GAN, I can show a small demo of conditional GANs. I'll not explain the code, but and that's not for lung images. That's simply for creating handwritten numbers. So the output there will be much better. I'll change my screen. So I'll simply keep running the cells because there are certain cells with GIFs below. Here also I've connected to a T4 GPU, so I should be getting the speed here as well. Here I'm also going to use a visualization platform called TensorBoard. TensorBoard is basically a graphical visualization of the model being trained. So as we can see here below, so it has a lot of parameters which we can graphically see. So this graph is basically the different components of the model, and instead of changing the code, we can also change stuff from here as well. So as I had described before, this is the atom optimizer, this is the generator component, and this is the loss function, and stuff are labeled, and it's a very GUI way of changing things. And there are many kinds of distributions which are auto plotted here as well. um, and this is where I had imported the tensor board. These are again some constants that I had defined similar to the previous code. And latent dimension is again the input noise vector dimension. It's also called called latent dimension. MNIST dataset is something which is built into TensorFlow, so we don't need to download it. We can just take it from keras.datasets API. And there are plenty of datasets which we can also see over here. MNIST is also present over here. This is again the cell for defining the discriminator and generator. Now, instead of having one code line for each kind of layer to be added to this, they have simply passed in the layers as parameters to a sequential API, which is another way of doing it. And name, we can give a custom name to each model that we train. Now, this class conditional GAN is taking this model as input, and it's simply a class for housing the training loop for the conditional GAN. It has the gradient.tape function inside it as well. Now, this is the actual place where the training takes place, and this is the place where when I run it, I'll be able to change what kind of number I wish to plot later on. Um, there are various kind of histograms that are also shown here, and even for each layer, like the conf 2D transpose and conf 2D layers. So this gives a easier way for visualizing instead of training stuff on our own. So we'll need to wait a bit for the training to get over. And if once I try to go through the um, thing again, then one difference that I can see in the model here is this having a sigmoid activation instead of a tan H activation, because now the normalization is not same as before, and also the kernel size has changed over here, and the input sizes have obviously changed because we have reshaped it into a different size. And global max pooling 2D is another standard layer which is usually used after conf 2D for kind of averaging out the values, the pixel values in the thing. So now in the training steps, for each of them, the generator loss and the discriminator loss is being outputted, and the general trend is if it keeps decreasing. But one kind of red signal is when it keeps decreasing and suddenly the losses start shooting up, which is known as overfitting. So there are certain callback functions like this over here. This is a tensor board callback function, but certain callback functions can also be passed for causing early stopping of the training so that it doesn't overfit. And the minute the losses start spiking up, we can stop the training and simply get the model as it is at that step of training. So while I don't have such a callback here, since I'm doing only for 5 epochs, if it's like 100 epochs or so, it's usually there. So the training is over, and we can now use it for creating the predictions and the GIF later on. So here is where I'll be creating the image, and we can see it in progress. These are the various steps in which the generator is creating the image, the intermediate steps, and the final result will be quite convincing, which is very much like a 7. So if I wanted 4 over here, it's not as great as the 7 was, but yeah, this much sums that up. And this is again the tensor board visualization that I took you through before. So conditional GANs, as in the PPT I had shown before, they can be used for creating datas according to a certain kind of label that we want, and this can be useful for recreating labeled data sets from original patient data sets of the chest X-rays and other kind of diseases that we have. Uh, I think that's it for the workshop. Thanks a lot for attending.